Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Okay, so this problem we have here is a tricky problem. So we have a solenoid made out of a length of wire. So we have a length of wire that we know the length of. It has a length of L. And this wire is wound into n number of turns that are closely wound to make a solenoid. And by closely wound, they are looped. And they are so close together that they are basically touching. So we have many loops created from this wire of length L. So if we were to take two of those loops and make a circle, it would kind of look like that. But the next one is so close to it. This is a half circle, so imagine it continues to go around. Imagine the next wire is right next to it, so that they're basically touching, so that this distance here is basically 0. So now what we want to find here, so if we take this wire and look at it straight on, so if we take this little end and look at it, so it looks like you're looking into the page at the wire. So I'm going to make it really big. This is normally a really small wire, but we're going to open it up. So this is the wire made really big. And it continues on. So this is our wire. And it has a radius. So we have a radius, and we have the diameter, which goes all the way across. And if they are basically touching, the length of this wire is going to be, or the number of turns that we get, n, is going to be equal to the length. We have the total length divided by the diameter. That's n, the number of turns. So the number of turns we can make out of this length is the total length divided by the diameter of the cross section here of the wire. And that's because they're basically touching. So we have a diameter here, a diameter here, a diameter here. However many turns we have, we divide the length by the diameter and we'll get that. That's how many turns you can make out of that much wire. So that was one of the hard parts of this problem, in my opinion, is figuring out that. So what we want to find here is this radius, the radius of the internal wire here, the inside of the wire, how thick it is, basically. So we have an equation for a solenoid. Let's start by writing that out. So we want to find the radius of this wire. We have a magnetic field from a solenoid is equal to the permeability of free space, or mu naught, multiplied by the turns per unit length, lowercase n, times the current running through the wire. So the current would be little electrons running through this wire. That is the current. So that's the current we want, is the current running through the wire that travels around the solenoid. And we have an equation. This is our equation for a solenoid. So the next step here is to break up this little n. Because we have this equation here with big N. So let's break up this n. We know that the little n, the number of turns per length, is equal to big N, the number of turns, divided by the length. So we already know here, we already figured out what the number of turns is. We don't need that comma. So the next step here, we can write little n is equal to the length. Now the diameter is the whole length all the way across. So if we complete this, we get the diameter. But we want the radius, so let's write out the radius. We know n is equal to L over d, which d is just 2 of the radiuses. It's 2 times the radius. 2 times the radius. That's a radius and not an n. Radius. All of this is still divided by this L, which will end up canceling with this L. L divided by L, we get a 1, which means our little n here just ends up turning out to be 1 divided by 2 times the radius. That's our little n. So we can plug this back into our magnetic field equation. B is equal to mu naught times I divided by 2r. Okay, so we have an equation now and it has the radius in it. That's good because that's what we want to find is the radius. But we also have this I, the current. We don't know the current. That's not one of the things we're given. Of the things we are given, we have that we haven't used yet. Let's go back up here. We have well, let's not write it there because we're not given n. We're given the length. We have L. We have the magnetic field. We have B. And we are given the voltage used to create the current. That's a capital V. Write it as a capital just so we don't get it confused with velocity. So we have these 3 things. And now we have n too. We have n and little n. But we still don't know what R is. So we have the voltage. So here's another tricky part for this problem. The resistivity of silver. We're told we have a silver wire. The resistivity, abbreviated as rho, the Greek letter rho, is a constant. And I'll give that to you here, which is, it's readily available. They might have resistivity in your book, or a simple Google search will give it to you. Resistivity of silver, which is the compound we're using here, is 1.59 times 10 to the minus 8th, or to the minus 8. This is the resistivity of silver, abbreviated as rho. And this is in units of ohms. Ohm meter is the unit for it. Ohm is the Greek letter omega. So it's an ohm meter. Not an ohm per meter, ohm times meter. So there is an equation for resistance from resistivity. And that's the resistance of a substance with a known resistivity is equal to let me double check real quick. It's equal to rho times the length that you have divided by the cross-sectional area. So we want the resistivity of the wire through which the current is flowing, because we want to relate this to our V. We're we're given the voltage. We want to relate this resistivity to that to find the resistance. So it's resistivity times the length divided by the cross-sectional area. The cross-sectional area means the area of like if you were to cut this wire or look at the very tip of it. This is the cross-sectional area here. And the equation for the cross-sectional area of a circle, or it's just the area of a circle, is pi times the radius squared. And this is the same radius that we solved for, because the radius that we have in our equation is from the diameter, side by side, which equals the length. So this is the same radius. That's what the area equals. So we can rewrite this equation for R. The resistance is equal to resistivity times the length divided by 2 pi times the radius, or 2 times the pi times the radius squared. I'm confusing it with the circumference. We have pi times the radius squared. That's the cross-sectional area of our wire. So let's go back to where we were. We have B, now we have R. We need an equation that relates V and R, which we do know. We know that V is equal to IR, but we can rearrange that to solve for R. Actually, we want to solve for I in this case because we want to get rid of our I. So if V is equal to IR, then I is equal to V over R. That's just simple algebra, just rearranging the equation. This is the voltage divided by R. Let's double check that we did algebra right. So we have V equals IR. We want to find out what R is. Yeah, so we divide both sides by R. So I is equal to V divided by R. Never hurts to double check. So now we have I, and we can plug in this value for R here. This is what R is equal to that we already solved. So let's plug in all of this stuff now into our equation. So now we have B, same as always, same as this equation here, is equal to mu naught times I. I'm going to write it in parentheses just so you can see that I is equal to all of this stuff. So we have our V, our voltage, divided by R, which we know that R is equal to rho times L divided by pi r squared. This is, all of this stuff is I. So it's a big jumbled mess right now. That was our I, and now in the denominator here we still have 2 times the radius. So let's look at what we have. We know what B is, we're given that in the problem. Mu naught is a constant. We know rho, that's the resistivity of silver. We know the length, we know the voltage, we know pi, that's a constant. And all that's left is the radius. So now we just have to do some algebra here to solve for the radius, and we'll be all set. So let's clean this up a little bit. So we can move mu naught and V over to the other side to make this look a little bit nicer first. So to do that, they're both in the numerator here, we just divide both sides. So we have B no longer by itself, divided by the voltage times mu naught. That's the left-hand side. Right-hand side now looks a little bit better. we have so now we have in the numerator part, we have two fractions here. We have a complex fraction. Rho L divided by pi r squared. I'm sorry, that's a little r. Little r squared, all divided by 2r. So let's change it up again. Do some more algebra. So to move this and get rid of this complex fraction, we can flip this. In that case, we'll end up with, let me do the left-hand side first, just so we don't lose track of what we're doing. V times mu naught let's move that 2 over. If we multiply both sides by 2, we'll get the 2 up here with the b. Just trying to save a couple steps here. So now if we flip this, it looks like this. We have pi r squared divided by rho L, the length. All this now divided by r. So we want to get just the r's on one side so we can solve for it. So now we have here this complex fraction. We can cancel this r with one of the r's here, because r squared is r times r. We can cancel one of those r's with this r down here. And if you want to see that, you can write this r over 1 and then flip it to get it up to the numerator here, 1 over r. And then that r will cancel with the squared here. So we can rewrite this again as, I'm going to move that pi over here now. We have 2b, divide both sides by the pi to move it over. We have, let's put our constants outside, divided by pi times mu naught times the voltage. Now this is equal to the simplified version of this. All we have left, we got rid of pi, we have an r, because we only canceled the square, divided by rho times L. So now for the last step, I'm going to flip these so we have r on the left-hand side. It's just a pet peeve I have. So we have r now is equal to 2 times the magnetic field times rho times the length. All of that divided by everything we have here. We have pi times mu naught times the voltage. And this is the radius. Now the radius that we solved for is the radius for the cross-sectional area of the wire here. We solved for that radius. And now we have that. We have an equation with everything that we're given. We know everything in this equation. Just plug in your numbers, and you will have the radius solved for.